Hey everyone, Active Learning here. Welcome to my YouTube channel. In today's video, I will be providing an introduction to deep learning. Alright, so let's get started. In this video, we will cover the structure of a perceptron, weights and bias, neurons, hidden layers, activation functions, for propagation, loss function, optimizers, especially gradient descent, and finally backward propagation. And if you're not familiar with any of these terms, don't worry, we'll cover them in the video. So without further ado, let's jump right in. So let's first define some key terms that will be used throughout the video. And here we have neuron. And you can think of a neuron as a function that takes in multiple inputs and it outputs a single output, right? And layers are simply a collection of neurons with the same operation, include the same hyperparameters. And if you're not sure what hyperparameters are, they're basically parameters that we can change by ourselves. So any parameters that the machine doesn't change, that humans can change, right? For example, learning rate is a hyperparameter that we can change by ourselves. Okay, and finally we have hidden layer, which are basically any layers in between the input layer and the output layer. So let's see a visual representation of what we have just discussed. So here we have three blue dots, and the three blue dots are called the input layers, and these three blue dots are neurons, right? These are the input neurons. And we see that we can take inputs. We input values into these input neurons, and the red dot is called the red dot is part of the hidden layer, right? And this red dot is also a neuron. And finally, we have the output layer, which is this yellow dot. So we can connect all of these neurons. And finally, we get the output. So how it works is that we take some inputs and we feed it through the hidden layer 1, and this neuron will output a number and it'll pass it through the output layer, and finally that will give us our output. Okay. And let's say that we have a simple data set. For example, we have play, study, sleep, pass, and fail. So, for example, a student plays for 3 hours, he studies for 7 hours, and sleeps for 7 hours. We can assume that he passed, right? But another student might have played for 5 hours, studied for 2 hours, and slept for 8 hours. We can say that they failed. And so on. We have another one here. So that's our simple data set. Let's see how we can use that with our neural network, our perceptron, which is basically a single layered neural network, right? Okay, let's see. We input the features. We have play, study, and sleep. We input it into the input neuron, and we feed it through the hidden layer. And finally, we take that value and then we feed it to the output layer, and we get our output, right? And this is hidden layer with one neuron, output neuron, right? Okay. Now, your input can be many different things, right? It can be voice, it can be text, it could be an image of like taco, food, whatever, right? It can be a lot of different things. And before our model works with the input data, we need to transform the inputs into numbers. Machine learning, machines only work with numbers, right? It's hard for a machine to work with something like images. So we have to transform our images into numbers so that our model can actually learn the pattern between the numbers. Okay. And so we have these inputs. We have voice, we might have speech or text, and we have some images, right? And we transform them to numbers, right? This is how it might look, right? And this is called a tensor if you're wondering. And we need to choose the appropriate neural network for our problem. We input the numbers. Um, this is after um, we transform our input into numbers. We use the numbers, we input it into our neural network like this, and we get our output at the end. Okay. Let's see our representation output. It's also numbers. So we don't actually immediately get back an image or a text or anything. We actually get back numbers as well for our representation output. So that's something that you have to keep in mind. Okay, and we take those numbers and then we decide whether it's pizza, traffic, or even, hey Siri, what's the time? And these are typically probabilities, right? And you'll see later on how these work. Perhaps, maybe not in this video, but I would definitely discuss how it works in later videos. Okay, and let's go back to our example of our simple perceptron, right? And we have to multiply our input by something called weights. And what weights are, they simply change how much the input affects our output, right? That's a simple way to think about it. And so we have to multiply play by weights, we have to multiply study by weights, and we have to multiply sleep by weights. And then we take the sum of those and we input that into our hidden layer with one neuron. Okay. And let's have our example again, but this time we are gonna have two neurons in our hidden layer one. And this is still called a perceptron because we only have one hidden layer, right? This is still the perceptron, except we have two neurons and we still have our output neuron here. And it's important to keep in mind that you have to connect all the neurons or else the neural network won't work. So that is something important that you should keep in mind. And here, let's go in more details on how our simple perceptron works. So let's say our input are x1, x2, x3, and we have to multiply these by weight 1, weight 2, and weight 3. And here, we take the sum. This is basically saying taking the sum of input times weight, input 2 times weight, input 3 times weight. We take the sum of these values. This is what this means, okay? And this is simply the same as that, right? Input times weight. And then we finally have to add in something called a bias term. And we have to add it to the sum of that. It's not included in this. We have to add the bias term to that. And finally, we take the sum of this and the bias term, we feed it to something called an activation function. And what an activation function is, we can see an example. We might have this, which is called the sigmoid function, right? It basically turns this linear. This is very linear, right? This isn't like a curve or anything. We take this linear and then we feed it into our sigmoid functions so that it's more of a curve rather than linear. And this makes more sense if you understand logistic regression, which I made a video on a couple weeks ago. And I also highly recommend you to check out my linear regression video because that's sort of a prerequisite for logistic regression as well. So yeah. And this basically outputs a value between 0 and 1. So we can set a limit, for example, if the value we get after inputting into this activation function is greater than 0.5, sorry, then we should output 1, and otherwise we should output 0, right? and 1 and 0 basically means yes or no. So in our study case, it could be yes, the student passed, and or no, the student failed, right? And we do something similar with the output neuron here. Okay, and we actually have to multiply by another weight called weight 4 after we feed it into our neuron in our hidden layer 1. And this whole process, this entire process is something called the forward propagation, right? This process is called the forward propagation, where we're multiplying the input by the weight. We're taking the sum, adding the bias term, feed it into the activation function. We get the output, multiply that by weight, and we feed it into our output neuron, and finally we get our output. That entire process is called the forward propagation. Okay, now let's say that our output, our predictive output, after we feed into our neural network is 0. But the actual value was actually 1. Let's say that y hat is our predictive value and y is our actual value. So if we take the difference, we actually get 1. And that's bad, right? Our difference is 1. We are actually off. That's not the value that we want. So we need to actually minimize our difference. And we need to get it as close to 0 as possible in order to minimize the error that our prediction is making, right? So we should get this value to get this value as close to 0 as possible, because getting 0 means that we're making a perfect prediction where nothing is wrong. Okay? And this thing here is called the loss function, where we're taking the difference between the actual value minus the predicted value. And we're trying to minimize the loss function. So what do we do to minimize our loss function? Well, let's go back to our example here in the forward propagation. We actually perform a process called the backward propagation, where we update our weights, right? We try to update our weights so that we get a better output. And updating our weights, changing the weights, basically affects how much an input affects the output. And that's what happens in the backward propagation. But let's go more in depth, right? See, it's just updating the weights. And we update weights using something called optimizers. So let me explain what optimizers are. So what are some examples of optimizers? The most common example is gradient descent, right? How it works simply is that, for example, we start at a random spot on our weight versus loss plot, right? We're getting a weight and we're plotting it against the loss. And we start at any random point on the graph. And for our point here, we're trying to go down until we reach this point. So why do we want to reach this point? Well, this weight value here minimizes the loss. So loss in our case, right, is actual value minus predicted value. So this weight here will minimize the loss. And that's what we want, right? So we should descend until we reaches this value that minimizes the loss. Okay, so how might we do that? I think I'll cover more about gradient descent in my next video, which will be deep learning more in depth. But in this video, I'm just providing a brief overview of how machine learning works, how deep learning works, sorry. And there are a lot of other things, right? And this is just a simple introduction to perceptrons. And you might see other types of neural networks, such as RN and CN and AN, and we'll cover those in future videos for sure. Alright, so summary. We have the input layer, and we take our inputs, multiply our input by the weights, we add in the bias, and we take that value, apply to the activation function, and we're using sigmoid for binary classification, right? And if you're doing multi-class classification, you might use softmax, right? And softmax basically works better than sigmoid for multi-class classification. And then during our back propagation, we use something called the loss function, right? Which is the difference between the predicted value and the actual value. And then we use optimizers to update our weights, which we try to minimize the loss function by updating our weights. And finally, we update the weights. Cool. So forward propagation and backward propagation are extremely important in deep learning. And AN, CNN, RN, object detection all utilize forward and backward propagation, right? And if you're wondering what these terms mean, AN is artificial neural network, CNN is convolutional neural network, and RNN is recurrent neural network. And yeah, that's what they actually stand for. Okay, so here are some additional notes. Each dense layer actually manages its own weight matrix that contains all the connection weights between the neurons and their inputs, right? And to calculate the number of connection weights for the current hidden layer, you take the number of output for the previous layer times the number of output for the current layer, right? So we, yeah, I don't think I have an example for that, but you can sort of look deeper into this on your own. And so, and each dense layer manages its own vector of bias terms, right? One per neuron. So if your neuron has 300, so if your hidden layer has 300 neurons, then you will have 300 bias terms. And the sum of the number of connection weights and bias term is called the number of parameters. And our neural network actually tries to reach the best parameters. And remember that parameters are different from hyperparameters. Parameters are what machine learn our machine model is trying to learn to optimize for the best parameters. And while hyperparameters are parameters that we can uh, adjust ourselves in order to optimize our neural network, right? So that's the distinction. And so final summary, in this video we have covered the structure of a perceptron, weights, neurons, hidden layers, activation functions, and we cover sigmoid function. And for propagation, remember taking input multiplied by weight, feeding it into our hidden layer and output layer, and finally we get our output. Loss function, for our loss function we did actual value minus predicted value. And optimizers, we talked about gradient descent, but there are a lot of other ones, right? And the most common ones that you actually see are stochastic gradient descent and the atom optimizer. And they're really powerful, but typically atom is the most used one, and I think I would discuss atom in a future video as well. It's really important to know. And finally, we cover backward propagation, which is basically updating our weights through the usage of optimizers, right? Update our weights so that our model yields a better output next time. And for activation function, the most common one you'll see is probably ReLU activation function, which means rectified linear unit. And I'll definitely make a video on that because ReLU is pretty important, especially for it's pretty important for deep learning. All right. So yeah, that's everything. Thank you guys for watching. And if you have any questions that you're still uncertain about, please comment it down in the comments below because I'll be very happy to help. And yeah, if you have any suggestions for my future videos, please comment them down below as well because I am still learning how to make better videos and I would definitely like to improve my future videos. Alright, so yeah, thank you guys for watching and see you next time.